6-7 is all about the probabilities of unions. Earlier in the unit, we talked about what a union was, the combination of two or more events and their outcomes. So, how can we calculate the probability of a union? Can we just add the probabilities of the two events separately? Well, to take a look further at this, let's look at the example of a 12-sided die and two events. Event A, the factors of 6, and event B, the even numbers. The Venn diagram shows a picture of the two events and how they relate to each other. We have 4 outcomes in event A, and we have 6 outcomes in event B. Visually, the union would be the shading of both bubbles combined. And it would look something like this. Well, let's calculate the probabilities of each event. Event A has 4 outcomes, so therefore the probability would be 4 out of 12, unreduced. Event B has 6 outcomes, so its probability would be 6 out of 12, unreduced. So the question is, can we just add those up to calculate the union probability? Is the union probability 10 out of 12? Well, if you look at the Venn diagram, you can see that the answer is no. In the Venn diagram, we have 8 outcomes that are shaded in the shaded region. So the correct probability of the union is 8 out of 12. So why is this wrong? If you take a look at the Venn diagrams at the bottom of the first page, you can see why this is wrong. When we counted event A, we counted 4 outcomes, 1, 2, 3, and 6. When we counted B, we were counting 6 events. But if you notice, we counted 2 and 6 twice. So we were actually double counting any of the values in the intersection. So we need to account for this by taking away the intersection value. So if we were to take 4 twelfths plus 6 twelfths and then take away the 2 twelfths in the intersection, we would get the correct union probability of 8 out of 12. If we want to generalize this formula for any union, we're going to get the following formula. Probability of A or B will be equal to the probability of A plus the probability of B minus the probability of A and B. This is our new formula for the day and an important one to know. So let's go ahead and apply this formula on the next page. Here we have several examples. 1A, we want to determine the requested probability. We have the probability of A, we have the probability of B, and we have the probability of A and B. We want to simply calculate the probability of A or B. So we go to our formula, the probability of A or B. As we know, this is equal to the probability of A plus the probability of B minus the probability of A and B. Since we know the 3 pieces on the right, we'll go ahead and plug them in. A is 0.3, the probability of B is 0.6, and the probability of the intersection is 0.112 or 12. This will allow us to straight calculate the union probability, and if we do this, we will find that this probability is 78, or 0.78, sorry. Let's take a look at B. B gives us the probability of A and B, but not the intersection. However, it does give us this extra fact that A and B are mutually exclusive. So why is this helpful? Well, if you recall, mutually exclusive were 2 events that did not have any overlapping outcomes. Visually, in a Venn diagram, this would be two bubbles that don't overlap. So the question is, what is the probability of A and B then? Well, the probability of A and B for mutually exclusive events would be 0 because there is no overlap. There is no intersection between two mutually exclusive events. So knowing this, we can calculate the probability of A or B by using the formula. We start off with the probability of A plus the probability of B minus the probability of A and B. Plug in each of these values that we now know. Probability of A is 0.35 plus the probability of B, 0.27 minus 0. Adding these together, we get the probability of our union A or B as 0.62. Moving on to C. In part C, we know the union probability. We know A, we know B, but we're looking for the AND. So once again, we're going to start off with our union equation. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we're going to plug in what we know. This time, we actually know the OR probability. So we'll go ahead and plug in 0.74 for the left side. We know the A is 0.35, and we know the B is 0.6. But what we don't know is the probability of A and B. This becomes our variable, what we're going to solve for. In order to solve, I'm going to simplify first. So I'm going to combine the 0.35 plus the 0.6. If I do this, I get 0.95. Next, in order to solve for our probability of A and B, I'm going to get rid of the 0.95 that's on the same side by subtracting by it. If I take away 0.95 from 0.74, I actually get a negative 0.21. Now don't let this bother you because this is not our final probability. And on the right-hand side, I still have a negative probability of A and B. To get rid of the negative, you can think of this as a ghost -1 and divide by it to get rid of it. This tells me that the probability of A and B will be equal to the positive probability of 0.21. And that's our final answer. Looking at number 2, we want to again determine the requested probabilities. However, if you notice in the directions, we are given that the events are independent. This is extremely important because now that we know the events are independent, we can also use, if needed, the independent event equations, as I have listed here. Our AND probability and the two conditional probabilities. So please keep those in mind anytime you have independent events. So let's take a look at 2A. We have our probabilities of A and B, and we want to know our probability of our union again. So if you look at the formula, the union probability is A plus the probability of B minus the probability of A and B. However, we're missing that A and B. We need that A and B in order to solve for our union. So how could we solve for the probability of A and B? Well, as I had mentioned just a little bit ago, we know that these two events are independent. And because they're independent, we can use the intersection formula. The probability of A and B is equal to the probability of A times the probability of B. And once again, we can only use this because they are independent. If we fill in what we know, 0.1 times 0.4, we get that the intersection is equal to 0.04. Now that we know our intersection, we can find our union by plugging them into our union formula. Probability of A plus the probability of B minus the probability of A and B. Plugging in what we know, we have 0.1 for A, we have 0.4 for B, and now we can take away our intersection probability that we just calculated, 0.04. In doing so, we get our OR probability of 0.46. All right, let's take a look at part B. We know our AND probability, we know our B, and we still want to know our OR probability. So how could we get the OR? If you notice, once again, if you look at your OR formula, we need A, B, and the probability of the AND. So in this case, we're missing the A. We're going to do essentially a similar thing using the AND independent formula. A and B is equal to the probability of A times the probability of B. But this time we're going to solve for A. So we know the AND is 0.2, we don't know the probability of A, and we know the probability of B is 0.5. Now we can solve for the probability of A by dividing by 0.5, and we find that the probability of A is 0.4. Now that we know A, the probability of B, and the probability of our intersection, we can plug them into our OR formula and calculate the probability of the union. So the probability of A, we just calculated, 0.4, plus the probability of B, which was given, minus the probability of A and B, which was also given. Combining all of these numbers, we get our final union probability of 0.7. Next, let's take a look at part C. Here we have the AND, the A, and the B. So we have all three parts, and all we need to do is plug them in. Once again, A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Plugging in A, plugging in B, and plugging in the intersection probability. Oops, sorry, that should be a minus sign here. And calculating, we get 0.86. So C was actually pretty easy. They gave us all three parts, so all we had to do was plug it in. Now you'll note that in the directions it did say they were independent, and if you were to calculate the A and B by multiplying A and B, you would get 0.24 as well. So that also checks out that they are independent. So technically, they didn't need to give us the intersection. Let's take a look at example 3. Using a standard deck of cards, we want to determine the probabilities. In part A, we want to find the probability that we have a 4 or a black card. We're going to calculate the OR probability the same way we did with the previous problems, except with specific event names. So for a union, the probability will be equal to the probability of the first event plus the probability of the second event minus the probability of the intersection of the two events. So that's exactly what we're going to do. We're going to find the probability of the 4 plus the probability of a black card and take away the probability of the intersection of a 4 and black card. So let's calculate each of these probabilities individually. Probability of a 4. There are 4 cards in a deck of cards out of a total of 52 cards. I'm not going to reduce this because I'm eventually going to add these fractions, and they will each have a denominator of 52. Next, let's calculate the probability of a black card. Well, there are 26 cards out of 52 which are black. Last but not least, we're going to subtract the probability of the intersection, 4 and black. In other words, how many cards are going to be blacks and a number 4? Well, there are 2 black 4 cards, the 4 of spades and the 4 of clubs, out of a total of 52 cards. Adding and subtracting these numbers, 4 plus 26 gives me 30, minus 2 gives me 28 out of 52. So this is my probability, and as we know, we should reduce our final answer with probabilities. If we reduce this, I could cut it in half, 14 out of 26, and I could actually cut this in half again and get 7 out of 13 as my final probability. Or you can also give the decimal equivalent or the percentage. Let's take a look at problem 3b. Probability of a face card or a spade. Again, I'll write the equation first. For a union, we're going to have the probability of the first event, so a face, plus the probability of the second event, so in this case a spade, minus the probability of the intersection, face and spade. So let's talk about face. There are 12 face cards. So we'll add 12 out of 52 plus spades. There are 13 spades out of 52 minus face and spades. Well, in our suit spades, we have 3 face cards. So 3 out of 52 will be face and spade cards. 12 plus 13 gives me 25. Take away 3 gives me 22 out of 52 cards. Again, we want to simplify any fractions, so I get 11 out of 26. You could also give the percentage or the decimal equivalent as well. And that's our final answer.